All right, a couple more sections. Hopefully they'll answer some of the questions that I got asked at lunch, because I think a lot of them are in these dashboard and then the return on investment section. So we've talked a lot about dynamic lighting. We've talked about dynamic HVAC systems and dynamic exhaust fans. So how do we keep track of all this? How do we make sure these systems are functioning in the way that we intend them to function, that we're getting the return on investment? We talked a little bit about sub-metering earlier. We'll talk a little bit more about that now in the dashboards that we use. And so on the CDCV side and on the air side, we are dashboarding for things like this, air change rates. Obviously, we want to know what the flows are. So CFM delivery, CFM exhaust, those kinds of things. You have indoor air quality. So obviously, your environmental health and safety professionals, they have their own set of dashboards that they want to look at. Sash position of each fume hood. Nice thing is that, yeah, you're buying a system that trends indoor air quality, but it also picks up the valve position, so you're already getting sash position of each fume hood. All of these things can be trended and then can be used, again, going back and setting up those metrics that we talked about in the beginning and making sure that you're accomplishing what you set out to accomplish. And if you have something that's going wrong, well, then you're basically doing constant commissioning, and you're getting the chance to go in there and get those things fixed. So here's a really quick view of some of the dashboards that we use at UC Irvine. And this one happens to be from the CDCV system. And you're setting up a goal, a target air change reduction that you're trying to meet. But what's really interesting is if you're laying out 4 and 2, or if you have some labs that are 6 or some labs that are 8, or you're laying out an air change rate, you have an occupied and unoccupied air change rate that you're trying to target. And so we want to know, are we meeting those targets? If we're not meeting those targets, we want to know why. We want to know how often. We want to know whether we're meeting those targets in the occupied room or in the unoccupied room, and whether that makes a difference. So we can trend all this. We can trend it all very, very quickly using these dashboards. And you can just pull up any dash block you want and add it to the screen. But then what happens is you say, okay, how do I drill down? How do I solve my issue? So if I'm not meeting my target, how do I find out? Well, there's a dash block that's specifically designed for that on the air side. So what happens is that you can pull up a dash block that does what's driving my air changes in the room. And you can look and see, is it thermally driven? Is it fume hood driven? Indoor air quality driven? And so from there, you can sort those and then pick that out. Now, this looks like a horribly long line with lots and lots of energy waste. It turns out that it's 257 CFM over design, minimum. So it's not a huge energy waste. The fact is that building's performing incredibly well, and it's really, really close to meeting its targets. Just that room happens to be the worst. You could also then correlate the fact that that's on the south side of the building. It was probably getting daytime sun a lot. And so, yes, it's thermally driven more than some of the other rooms are. So if you look at another situation, you can say, well, what percent of the time am I having these issues? Is it 100% of the time? Is it 50% of the time? And so you can, again, go in and you can do that in occupied and unoccupied mode. What this allows you to do then is say, okay, every week I want to spend time chasing down my 5 worst offenders. Or if I have extra staff or I have something where I actually have people who can spend a little extra time, maybe I want to check out my top 10. But you basically are saying, let's make sure that we're staying constantly commissioned by writing work orders based on the information that I'm getting out of my dashboards. As far as the fume hoods, again, being able to run reports that give you data that you can pull and send out and say, how well am I doing? How well are the people in my labs managing their sash openings is a very difficult thing to do. A lot of times you'd see people send out, they'd want to have fume hood competitions. They send people out, they mark where they saw the sashes open. They go out at random times during the day. Students do this and stuff. Here it's all automated. Full sash position that sash operated over, and you can run this for the day, the week, the month, the year. So sometime over this period, and this is a month period, that sash went from 0% open to about 60% open. Then you have the averages. If it's a red bar, the average got worse. So this sash was average open at about 10% open. It's probably now average open at about 20% open. So it tells you that the average has gotten worse. This one over here, which is on a 3rd floor, and it was kind of being ignored. I watched it stay open for about a month, and then I finally said, I'm going to drive over to campus. I'm going to go to that room. I'm going to close that sash. So the nice part is this doesn't just trend a vertical sash. It trends combination sashes. So what this actually was is the sash was closed. Somebody knew what they were supposed to be doing, but the combinations were wide open. So the horizontals were, you had your full gap. So went over there, closed this, and you can see the green indicates the average got much, much better. But imagine being able to run this and then sending it out floor by floor or lab building by lab building as an email every month. Not only do you see your own lab, but you see everybody else. And if you're the worst offender, you're probably going to make changes. Again, going back to saying what's driving my air change rates. If you pull up that first dash block and you say, wow, I'm flowing 15 air changes in that room, I wonder what's going on. Well, it might be because you have a sash load. And so if it's sash load, you might say, well, is it one sash driving that, or is it two sashes? What's going on? So I can see in real time what's going on as well. It's all actionable data, and that's what these dash blocks really want to give you. So when you think about, well, do I like UC Irvine's program? What parts of it do we want to implement? It's how much data do I have about my laboratories now, and how much information do they have? Is that helpful just from an energy side? Is it helpful from an EH&S side and an energy side? Is it a complete sustainability group? We don't just keep these dash blocks within facilities or within facilities in EH&S. As I said earlier today, we share all of this information. All these passwords, all the logins, given out every time we do one of the town halls. They can all come and see this information. So here's total flow. This is looking at an entire building. Again, this isn't a dash block. This is actually an export of the data from another part of the system. But it's very, very simple to do. And what we're doing is we're saying, yeah, 2 and 4 air changes, 2 unoccupied, 4 occupied, but it's not static. It's not a static system. Call for cooling, sash position, all of these things are inputs to the system. It's very dynamic. Well, if it's very dynamic, what you result in is a very dynamic air change rate and a very dynamic change in total CFM supplied to the system. And so you can see it averages somewhere between 3 and 6. But 3 and 6, 6 being my peak, is still much lower than setting my minimum at 6. So when you hear, yes, they're running at 2 air changes, or they're running at 4 air changes, we're not really running at those numbers. That's just the minimum. Everything else is an input. So here you go. Here's a typical lab profile. Maybe not typical, maybe atypical lab profile, because we have these large spikes. This is one of those biosafety cabinet rooms from Gross Hall that I showed you earlier today when I was talking about the sub-metering. And we said, we're getting these spikes. Something's going on out here. We need to visit that laboratory. We need to understand what's taking place. They're not long-lasting. It's very, very short bursts of increased air change rates. But they're doing something, and it's not obviously being captured by a fume hood or a snorkel or one of those things. It's going into the general exhaust. So we go out to this space, myself and David, and we visit with the PI, and we said, excuse me, here's this graph that we have. We see all of these spikes taking place. What are you doing? What could possibly be happening that's triggering a volatile organic chemical event? And we don't know what the chemical is. We just know that the event is occurring. They said, oh, when we get down at the end of the day, we do stem cell research. We wipe down so we don't cross-contaminate our research with this Windex bottle of 70% ethanol, 30% water. Spray it all over everything, floor, walls, everything, wipe everything down, move on. So that's exactly what the system's seeing. It's seeing this huge VOC event, and it's able to clear it incredibly quickly because, it's obviously, 12 air changes, 15 minutes. That's a lot of air you're flowing through that space. And, alcohol evaporates very quickly. So this is what you're seeing. But again, interesting data that you can't necessarily pull otherwise. What did it do? It generated an environmental health and safety response. It also generated an energy manager response, because I'm like, why are we doing this? So, again, it's something that actually generates a response. You probably don't have that ability right now. This is what the savings looks like from facilities management at UCI's perspective, because we base it on 6 air changes. If you base it on 8 or 10 air changes per hour, your savings are enormous. Now remember, it's compounding, right? It's not just the supply fans, it's also the exhaust fans, it's also the reheat energy. So you're talking about an enormous amount of energy. Trending of occupancy sensors. Everybody says their labs are occupied all the time. Maybe that's true, maybe that's not true. But isn't it interesting to trend the EUI versus the occupied hours of a space, right? So yes, that's energy intensive, but are they ever there? Those kinds of questions. They can all be answered here. That building utilization, how is that compared to another building on campus? Building load per square foot. Go back to the very opening topic. Yeah, it doesn't tell you a lot of information. Sub-meter that down and say, add my exhaust fan energy, my supply fan energy, my pump energy, my chilled water energy, and divide by building square footage. compare two buildings on my campus. One running at 6 air changes, supposedly, probably a little higher. One running at 4 and 2. One taking advantage of the reheat and everything else. And then say, yeah, I'm saving 1 watt per square foot, but then translate that to dollars. I'm saving 92 cents a square foot. So you can start to really break these metrics down, really understand how much money am I saving in relation to energy, and when am I saving that energy. We talked earlier, or at least I talked earlier, about the lighting design. And so previous lighting design standards, 1 watt per square foot. Pretty good average. That's not a bad lighting power density number. But when we did Gross Hall, we wanted to be at 0.6 of a watt per square foot. Really low lighting power density. Okay, so how did that work out? Are people conscious of their energy needs? So again, let's compare two buildings, and let's see how that works. In fact, you can even see that when people go to lunch here, you get a little dip. So you can even then, again, translate that back to dollars. So now I've shown you between two different measures, almost $1.17 per square foot in energy savings per year. Siri's busy, sorry. Comparing two similar floors, Hewitt Hall and Gross Hall, we heard Wendell talk earlier about how quickly we had to build that stem cell building when the money became available. What we took was a successful lab building on our campus, which was Hewitt Hall. We flipped the floor plan and added a floor. Other than that, they're the same designs. Now, the nice part is we added a bunch of smart lab features, as he pointed out, because we were trying to get to 50% energy savings over Title 24. So you have very similar floor plans, which means you have very similar labs. So if we to look at these two labs, one running at 8 air changes, no setback for unoccupied, these kinds of things, versus the Gross Hall lab with the really good lighting design and everything else that we looked at, let's look at the airflows. We saw this line earlier. That's where I got that VAV slide from. That's a VAV building running as a constant volume. Here's that same laboratory in the building next door on the second floor, and look how dynamic it is. And now, as opposed to the room that I showed you earlier with the biosafety cabinets, you can see this one has fume hoods, so you do actually drive the air change rates up now and then. It's just really, really interesting data that allows you to look at it quickly and maintain it. So what does your energy dollars and energy spend look like when you look at a CFM per square foot of that Hewitt Hall versus Gross Hall? Well, yeah, running that high air change rate and not taking use of your VAV system, you're never going to pay it back. Gross Hall, you'll pay back. It works out really, really well. So what if we take the two systems, we combine their data, and we go to big data analytics, right? So we take the HVAC data that we're getting from the CDCV system, we take the sub-metering data, and we start popping those on top of each other. And we say, all right, we know what our sash demand is here. We got our air change rates. We got the delta T of our air, right? So the temperature of the air supplied versus the temperature of the air exhausted. How much did I heat that air up while it was spending time in the room? So as sash demand goes down, you'd expect your air changes to go down. And as plug load goes up, you'd expect your air changes to go up as well. And you expect your delta T to do the same with these two things. Anything on this left-hand side of the graph, sash and indoor air quality driven reasons to have a high air change rate and a low delta T. In the center is where you want to be. And on the right side, you probably have a very high delta T, but you might also have high air change rates. And that's because it's plug load and lighting load governed, most likely. You remember we showed you those freezer farms. So let's dump our sub-metering data over that, and let's see with 130,000 data points where we're at. And what it turns out is that you can start to see very few things that are actually, based on the data that we were able to collect, SASH and IAQ driven, a little bit of plug load driven out here. But the majority of the data that I was able to collect when we were looking at this information shows that we're right in the optimal region. And 2 air changes was what we were basically minimized at, right? So let's say that we're outside of that graph. Let's say that we're working in this area or this area. Well, then there's solutions that you can quickly go to and say, all right, well, we should do these things. Maybe we have over-engineering. Maybe we have poor indoor air quality practices or bad sash management. Well, hopefully we can change those things. Over-engineering might mean reducing the air changes per hour as a minimum. On the other side, maybe we have lots of concentrated equipment that we can spread out across the lab. We can take advantage of the fact that we have a minimum air change rate by not concentrating the equipment so much and spread that heat load out, not being cooling driven. The other things we can do is things like adding spot cooling, chilled beams, fan coil units, those kinds of things. So it's an interesting way of taking not only your dashboard and your data that you're collecting from your CDCV system, but you're also taking your plug load system, sub-metering system, and combining that data. So if anybody tells you sub-metering doesn't save energy, I'll say, well, no, look, I can show you how it saves energy. It tells you where to go move things around and save energy. So what are we doing? We're really constantly and continuously commissioning our lab building, something that is not easy to do. You probably went out and spent $200,000 to $300,000 to have a consultant come in to do this work for you. The problem is that you get to the end of that, the consultant takes their toys and they go home. They give you the report that your building's back to where it should be, but you're left to run blind again. If you invest the way we did and you put the program in place, not only from an environmental health and safety perspective, but from a facilities management perspective, you now have all of this information feeding into you. Yeah, you probably have to reassign some duties and get people to actually look at this stuff, but you can see just about everything that a consultant will come in and tell you as part of a commissioning program of what to fix, where to fix it, and why it broke, and how to better optimize your building. It's all here. All that data is available. On top of that, you can troubleshoot things that you could never believe you could troubleshoot before. Gross Hall, CO2 delivery system with 4 tanks, the valves there. There's one of these on each floor. They connected this up, emptied in about 8 hours. Not me, not environmental health and safety. PI in the lab said, hey, that system that they installed senses CO2. What if we just plot every room? We'll find out where the leak is. We don't have to go soaping lines and trying to figure this out. So they did. And you can see, yeah, the colors are pretty tight and they repeat, but you can drill down in. You can figure out what room has the leak of CO2 from that system. Then they connect an air compressor, soap the lines in one room, identify the leak, fix the leak, put the system back in place. Another example, constant, that's not really commissioning at that point. That's just troubleshooting a building. We talked earlier about equipment, location, 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 right? So here's that foil on the desk. Here's a hot plate under a thermostat. I don't find hot plates on thermostats very easily by going out and walking lab buildings. It takes a lot of time to do that. However, I can look online and I can see, now this is weird because the time scale's moved, but you have high airflow, drops straight off, low airflow, straight back up to high airflow. So what is this? This is professor sleeping, professor in the morning working, and then sleeping again. So what happens is you have somebody coming in and turning this piece of equipment on, running it all day, not understanding why it's blasting air conditioning on them, and then turning it back off. And we get a cold call. Hey, I'm too cold in my laboratory. So we went out there. We said, hey, here's your problem. We just moved this hot plate. They said, well, hot plate's next to the fume hood. We move stuff from A to B. So we move the thermostat. Yeah, these things happen, but that's working in facilities at a university, right? Return on investment. We talked about commissioning and we talked about smart labs so far. So you have an initial investment with commissioning, right? And you get a return. You get your building performing better again. You get an energy savings. The only problem is that savings is compounding. That savings that you're getting every year is falling off. And then after 7 or so years, you have to make that investment again. And then you get your savings and it falls off again. The cycle keeps repeating. What if it didn't fall off? What if you were able to put a system in place with a larger initial investment, so investment much bigger, but it doesn't fall off, and then I look at how my savings go. So that's what we're really hoping happens with our program, is we don't want that to fall off, and we don't want to have to make that reinvestment. If anything, we just want to invest the dollars in keeping the system functioning as it should be. If we stack those next to each other, it becomes a no-brainer. Yeah, I'll spend the bigger dollar up front to put in the metering, to put in the CDCV system, to do the exhaust stack discharge velocity reduction, to fix the lighting, to do all that stuff. And then I'll just maintain it myself. The savings after, 10, 11 years, $1.2 million on this instance. They're big numbers. So let's go back to our very first slide, or one of our very first slides. These are my list of buildings again. All right, let's look at the results. They're not bad. 57% average kilowatt hour savings in the building. 72% average therm savings in the building. Why? Took all that reheat energy out. Yeah, huge numbers. 61% total average energy savings. They're big numbers. This works, the system works. Our climate is favorable, it does help. I don't have runaround loops, I don't have heat wheels, I don't have any of that stuff to worry about. We do have a nice ambient outside temperature, But what I'm saying is if you're starting with a higher air change rate, as you heard today, you can get these kind of numbers because even though we went from like 7 or 8 air changes per hour down to 4 and 2, you might be starting at 10 or 12. In addition, we talked about how these buildings were already better than code. Some of them, like this one here, LEED Platinum. Again, you can get points for bike racks just as easily as you can get points for energy savings. So, you know, just because it's LEED Platinum doesn't mean that you can't go out there and squeeze out a few additional energy dollars out of that program. And then, of course, the other tangible effects that you get from it. You get motor and bearing wear decreased. It's a deferred maintenance savings. As soon as you do this, you've cut how fast that fan's running. It's going to last longer. N+1 opportunities. Talked about a couple different ones. You have the N+1 opportunity of going to a manifolded exhaust fan so that hopefully when you go to service that exhaust fan on the roof, that you can take it offline and keep that fume hood in service. You don't have to take a fume hood outage. Higher research hours, higher ability to get work done without taking outages. So on top of that, failed component detection. I have all those dashboards. I can see stuff happening now. I know when there's issues that are taking place in my system. If I know those things, that's an increased safety. Hey, work order, go fix X. That Phoenix valve hasn't moved in a week, or that lab air control valve hasn't moved in a week. I know something's going on out there. It's really, really hard to see a lot of that stuff in the laboratories that you currently usually have to work and operate in. And then lab oversight, right? Hood management and chemical excursions. A lot of people might have hood management. I doubt very many of you have chemical excursion monitoring. Do you know whether or not chemicals are being released into the general dilution ventilation of your laboratories? And just guessing at an air change rate that's going to take care of that is probably not what you want to do. So conclusions and wrap up. Yeah, there's a future of what we're doing. We're not finished with our program. We have a few more lab buildings on campus that we can implement these things in. And we're working to make improvements on the system all the time, whether that's improvements on the IH side of how we go in and check out the labs, how we monitor the chemical inventories, all of those kinds of things, or improvements on the energy side with getting better dashboarding, getting better metrics, being able to sort the data faster. We're constantly looking for those things. One of the things that we've identified is you have these high volumes of ductwork, but you now have really low velocities of air. Why am I paying the static pressure penalty for having duct noise attenuators? Those are only in there because you had really high velocity air. So if I can go through, identify opportunities to go from a piece of ductwork that looks like this, where we're going to try to knock the noise down, to a piece of ductwork that looks like this, there's energy savings to be had there. LED lighting. LED lighting has come a long way. LED lighting is currently undergoing, you know, basically what computers did 10 years ago, where every 6 months you're like, why did I buy that? Because the next better one's out. So we have definitely started to move forward in this area. You've seen it in our task lighting, our campus wall packs, our exterior lighting, corridors. We see this. We're now starting to actually move the LED lighting into the lab spaces. This is one of those systems that we've been experimenting with. It's low voltage wiring, Cat5 wiring, power over Ethernet. Each sensor, each light fixture has its own occupancy sensor. It's feeding all of that data back. You can do all kinds of interesting things. You can set up basically lighting design. So you know, I walk into my office, I say, I only want them to come on to 80%. So all my lights only come on to 80% every time I walk in, but in the event the fire alarm goes off, lights go to 100%. Things like that. So, and this is the dashboard for that. Again, having that tracking, trending, and dashboarding capability. Lab display units. David showed you some lab display units earlier. We've been working with Android tablets and trying to improve upon that. Let's go from the dot matrix green screen display with 4 air changes versus how many ever with occupied, unoccupied, to actually being able to look across the room and see red when you're unoccupied, green when you're occupied backgrounds, and then being able to trend all of that information right in your lab. On top of that, let's say you're the fume hood loser of the month, and you don't understand why you're the fume hood loser of the month every month. You can go up to your Android tablet and say, how do I save energy with fume hoods? It'll play a video that it pulls right off of YouTube. It shows you closing the sash saves energy, and maybe goes through a whole talk as to why, you know, explains what a VAV system is and all of those things. Huge technology jump. These tablets are incredibly cheap. They're down to like 139 bucks. So again, you can see that we can even take existing dashboards and put them right onto the tablet. So, wrap up. Complete the prereqs. I think we went through all of those. I think most people know what they are. Safe air change rate optimization, understanding that, yeah, we're looking at not just a hard number, but how does that air move through the space? Fabric air diffuser was one of the things Mark showed you. Efficient lighting, being able to say, you know, not only is my lighting efficient, but do my people have the ability to take action on that lighting system? Do they walk in and get 100%, or do they walk in and get 50%? They have to take a manual action to bring it up to 100. ESDVR, exhaust stack discharge velocity reduction. Your exhaust fans are using a huge amount of energy if those bypasses are open. How do you know if they're open? Go up on the roof sometime, take a look. It's really easy to tell. Pressure drops. Pressure drops are something you can do right at the end that we found to be a huge energy savings. You can also talk about things like the high-performance filters. It's a deep pocket, almost 1 foot deep pocket filter. You could save about another ½ inch of static pressure there. Fume hood standby. So ANSI Z9.5, take that fume hood when the sash is closed. You're obviously governed by the 100 feet per minute or whatever your feet per minute face velocity is, but when that sash is closed, you're usually governed by that 25 CFM per square foot of work surface. Do a study on that. Find out what works for your fume hood, what you can lower that number down to. The other thing you can do is a zone presence sensor on the front of the fume hood. So if in front of our fume hood's unoccupied, we drop that face velocity down to 60 feet per minute. And then continuous commissioning. Put somebody in charge of it, make it happen, stay on top of it so that you don't end up, you know, with a building that's so out of whack that you spend all this money on that you have to go out and hire that consultant. So with that, I think we're at questions and answers.